So thanks everyone who is here for coming. I'm really excited for this session. I think there'll be a lot to cover. Um, First and foremost, I just want to do a quick acknowledgement of country. So I want to acknowledge the traditional custodians of the land on which each of us here are on today. For the speakers, myself and Patrick are on Gadigal land. Sam is on Bunurong and Wiradjuri land, and Peter is on the Yagara and Turrbal land. And I want to pay respects to any Indigenous people we have here today, along with elders past and present, and acknowledge that this land has been a place of learning and communication for millennia, and hopefully we in some small way can continue that tradition. So first up, as speakers, we have Peter. Peter is a UQ Amplified lecturer specializing in the philosophy of science, particularly in the philosophy of physics. His research interests include time and causation in modern physics, especially quantum foundations, and the epistemology and methodology of science. Peter's talk today will be work examining the relationship between notions of physical time and manifest time, and showing how the apparent conflicts between these two notions can in fact be reconciled. To do so, Peter re-examines our understanding of clocks and the relation between agents and the world. Take it away, Peter.
Great. Thanks very much for that, Jules, and thanks for organising, and thanks for those that have come along for coming along. Okay, let's get cracking. So the idea here is to try and give a physical basis for manifest time. I have collaborators. These are my collaborators: Sally Shrapnel, who's a lecturer in physics and also a philosopher at UQ, and Jerry Milburn, who's an emeritus professor in physics at UQ. This is the second part of a project we've been working on. So here's the target. This is Craig Callender. And I don't mean to pick on Craig in particular. I'm taking Craig to be an exemplar of the sort of view that I'm talking about. And in his book, his 2017 book, What Makes Time Special, here's an example of the sort of phrase that I'm interested in critiquing. Physical time departs dramatically from manifest time. Now, by physical time, which I'll say a few words about in a moment, Craig here means the image of time that we get from our contemporary physics. And by manifest time, this is kind of borrowing the word from Wilfrid Sellers, who spoke about the scientific image and the manifest image. Manifest time we take to be characterized by a past-future asymmetry, the fact that the present is special, and that time flows. So these are the three conditions that we take to exemplify manifest time. And this quote here is that physical time departs dramatically from this. So that is, physical time does not give us these parts of manifest time. But here's an interesting quote also from Craig's book. To be clear, I think that we can explain why manifest time arises for us in a world governed by our physical laws. But doing so, if I am right, will require embedding a subject like us in a world like ours, and not simply finding some structure in physics that plays the manifest time role. Now, this is very interesting because Craig then does not go on and do this in his book. And Sam Barron and I have a paper from a couple of years ago where we look at some of the arguments in the latter half of Craig's book that probably could have used a bit more of this and a bit less of the way that Craig went about it. I think that even in the earlier part of his book, same story goes. So actually what I'm going to be doing today is talking about how we complete this project by thinking about the role of embedded agents. Now, when we think of physical time, what we usually think of is something like this, kind of time dilation, this special relativistic Einstein picture, something like space-time, a general relativistic space-time, or perhaps something like cosmology, where we have our cosmological models that says we have a finite beginning, I should say a bounded beginning of the universe. And in these pictures of time, we don't seem to have these elements of manifest time, this asymmetry, this privileged present, and a flow, a time flow. So here's my argument. Now, I should preface this by saying This is a bit of a work in progress, so there's going to be more questions than solutions. And it's also highly speculative. And I'm aware of how speculative it is, but I'd be interested in what people think as we go. Hopefully we'll get some time for some questions. So the argument is that we've been looking in the wrong place for physical time. Relativity is not the right place to look to find our physical image of time. And I'm going to lean on an argument from Janan Ismail that is against globalism about laws. I'm also going to argue that we've failed to appreciate the relational nature of time. So Einstein famously said, time is what clocks measure. Now, I'm not going to be as blunt as that, but I'm going to have a look at the nature of clocks to find physical time. In particular, physical clocks, real clocks, are open, dissipative systems. I'm also going to say that we should be understanding agents as learning machines. So we've got a model of an agent as a learning machine, and our model shows that learning machines are necessarily physical clocks. That is open, dissipative systems. So with all these things combined, I want to show that when we look at an embedded agent modeled as a learning machine, then we've got grounds to say that this physical system shows us a time that aligns with manifest time. Now, it is a bit of a question mark because I don't think I've been able to show that just yet, but that's the goal of the project. So hopefully we can set it up and look at some of the problems associated with it. All right, now this is a very brief history of time, and as opposed to the title of Hawking's book, it actually is a history of time. So I'll be very quick about this just to contextualize some of the debate. So first of all, some of the major punctuation marks in the history of the physics of time. Newton, famous for absolute time. The Leibniz-Clark correspondence gives us the beginnings of relational time. And then about a century and a half later, Boltzmann gives us his ideas around the arrow of time. Now, I've got this highlighted blue. I'll explain that in just a moment. Beginning of the 20th century, we've got Einstein and Minkowski giving us this idea of space-time. In 1916, Einstein again gives us general relativity. In the 20s and 30s, we get this major discovery of Edwin Hubble, but then also the idea of the Big Bang from George Lemaitre. So that is a finite beginning. And then these general relativistic models, Friedman, Robertson, and Walker, that basically give us our modern cosmology that says time has a beginning about 13.6 billion years ago. And then at the end of the 40s, we get Gödel's famous solution to Einstein's equations of closed time-like curves. And this is probably the last major event in the history of the physics of time that concerns us. I then want to say a few things about the philosophy of time. Now, this is really not exhaustive. It's trying to just give a little bit of a 20th century history of where this is sitting. And I'll start with McTaggart, who essentially has set the terms of the contemporary debate with his A and B theories of time. Kind of pre-general relativity, we have this engagement from Russell and from Broad and from Roy Sellers, father of Wilfrid Sellers. I mean, I say pre-relativistic, it wasn't really until 1920 and the early 20s that we really get engagement with what the consequences of general relativity is. So these people aren't really engaging with relativity as such. But then we've got, I've highlighted these in red, these are physicists talking about the philosophy of time. Arthur Eddington was one of the people who wrote a tome on general relativity, and also James Jeans start talking about the philosophy of time based on relativity. And then by the time we get to the 50s, we get this explosion in the philosophy of time. Now, it's really only a couple of figures that I'm pointing out here. J.J.C. Smart and D.C. Williams. So Smart has his famous The Moving Now and The River of Time, and Williams has his famous The Myth of Passage. At this stage in the history, the attention is on relativity theory. So we have the philosophy of time now setting up what's become the contemporary debate. Can we find anything to do with our philosophical conceptions of time in relativity theory? I want to point out Grünbaum and Reichenbach as well. They also talk about the arrow of time. Now, these blue highlighted figures they're talking about thermodynamics. They're not talking about relativity theory. And it's interesting to note that Grunbaum and Reichenbach have both become figures in the history of the philosophy of causation rather than the philosophy of time, although they are kind of referred to in that context also. But by the 60s, we've now got proofs. We've got proofs from Reepdijk, Putnam, Malamont, from relativity to features of time. Now, my contention is that the contemporary debate focusing on relativity is the wrong place to focus. I guess I should say, if anyone has any punctuation marks in these histories that they think should be added here, please drop it in the chat. I'd be interested to know whether there's anyone missing that probably should be here in this very short potted history. So when we look at contemporary philosophy of time, and like I said, I'm not picking on Craig Callender, but his book is a perfect example. We get the debate is purely about what does relativity theory tell us about time, and then how do we square that with these philosophical conceptions of time? So, manifest time. All right, also in contemporary philosophy, we get an argument from Janan Ismail, how physics makes us free. And in this book of Janan's, she mounts an argument against globalism about laws. So I'm very quickly going to run through this argument. So it's against globalism. It's also against reification of our laws. So here's something that Janan says. Most day-to-day science is a study of open subsystems of the world that exchange energy and information with their environment. The laws of these kinds of systems tell us how they respond to various kinds of experimental interventions. They capture regularities that we can use to predict their behavior, or that we can harness to bring them to bring the systems under control. These are the most directly testable and most epistemically secure parts of science, right? So there's this strong empiricism that underlies Janan's philosophy. She goes on, philosophers often employ a rather different image of science. The image in question comes from focusing not on the local laws that describe the behavior of open subsystems of the universe, but on the emergent laws that describe the universe as a whole. It shifts the way we think of science in a subtle way. The earlier description made us think of scientific investigation as an active investigation between one open system, the experimenter, and another, the system under study. The focus on the global laws, by contrast, encourages a disembodied view of a closed universe, of which we ourselves are parts. And the earlier description made us think of the laws that describe the behavior of components of the universe as basic and the global as derivative. The focus on global laws, by contrast, makes us think of the global laws as basic and any description of the behavior of open subsystems as an incomplete description of the whole. She goes on to give the empiricist flavor of this in her book, in her publication, An Empiricist's Guide to Objective Modality. The result is a form of empiricist realism, so this is her story, a form of empiricist realism about modality that steers a path between reduction and reification. Claims about laws, chances, and other modalized structures encode inductions on observed regularities in a form that is tailored to solve the kind of practical and epistemic problems that beings like us, beings with limited sources of information about the world that gather and store information and use it to guide behavior, face. Right, so let's put all this together. Basically, this is saying the way an empiricist should view the world is in terms of these practical and epistemic problems. And it is in terms of these practical and epistemic problems that we get these local laws, and we abstract to the global laws, but we shouldn't reify these global laws. We shouldn't think that the global laws somehow prelude the local laws. It should be the other way around. And so there's a suggestion that perhaps this is why we shouldn't be looking to relativity to find out about what time is in the world. Right, so now I'm going to say a few words about a physical basis for time. So start to get into the argument. And I just want to point out this very lovely paper from Ruud and Zinkernagel. They're talking about a physical basis for cosmic time. They end up arguing that time has to be relational. And when we look further back into the universe, we can't find structures before about 10 to the minus 6 seconds that act as clocks. And therefore, we can't talk about time before about 10 to the minus 6 seconds. Now, while I'm not talking about that, it's a very interesting article. What they end up doing is they're saying it's difficult to find a reductive definition of time, right? So we might use that Einsteinian mantra, time is what clocks measure, but what's a clock? And then clocks coordinate coincidences between local events, but what's a coincidence if we don't know what time is? Right, so we've got this circular nature of clocks and time co-defining each other. So they came up with the time clock relation. And this is their time clock relation. There's a logical or conceptually necessary relation between time and a physical process which can function as a clock, in the sense that we cannot, in a well-defined way, use either of these concepts without referring to or presupposing the other. Right, so I'm going to take this sort of time clock relation to underpin, first of all, what time is, and second of all, what a clock is. So what sorts of physical processes then can function as a clock? And this is where, with my co-authors, we argue that a clock is, first of all, a local subsystem of the system it coordinates. And so time is relational. It is necessarily dissipative. And so it is necessarily irreversible. And so it is necessarily noisy and so prone to error. Right? So this is the argument we make about what a clock is. We go into this a bit further. There's a feature of these periodic clocks. It's called a limit cycle. And this is a natural feature of the global dynamical structure of the things that we think are clocks. And it constrains the system to a kind of self-sustained, stable oscillation. And when it arises under the circumstances when the work done balances the heat dissipation. So this is a thermodynamic effect. This is how we get a clock. Any physical system can be a clock. It has to have these features, these thermodynamic features. And we get uncertainty in the periods when we have low heat dissipation, and that uncertainty decreases as heat dissipation increases. So the higher the entropy, the better the clock, right? More entropy makes a better clock. So one way we might think of it is a clock is a flow meter for entropy. Another way to think about it is that a clock is a thermodynamic engine. Okay. Here's a little trivia for you. You've got until the time I finish the explanation to throw in the chat if you know the answer to this question. What is that in the blue circle? So this is to give you an example of noisy clocks. John Harrison was famous for solving the longitude problem, but before he solved the longitude problem, he made the most accurate clocks in the history of humanity. This one's from the 1920s, sorry, the 1820s. He had to put a panel on the front of the clock. A table of numbers is what this is. Does anyone know what it is? I'm assuming because no one's jumping in on the chat that people don't know. Right. This is the equation of time. And if you really want to be, have your mind blown, go and Google the equation of time. Check out the Wikipedia page. What the equation of time tells you is how you need to square an inaccurate clock, like this grandfather clock. It's 2 minutes off per 24 hours, with another inaccurate clock, a noisy clock, and that is noon to noon per day on the Earth's rotation. And the equation of time will tell you how you square those two things. So what we have here is two noisy clocks. One is Harrison's grandfather clock. The other is the Earth's rotation. We have to choose one to keep time by. And if we choose one, the other is inaccurate. But there's not some base clock that's underlying these things. So this gives you an intuition about noisy clocks. All clocks are noisy, and there's no master clock because clocks are relational. So can manifest time emerge from noisy clocks? Well, we argue that a noisy clock, a noisy non-interacting clock, will desynchronize more readily because it's noisy. Here's an example of a computer modeled 5 clocks that slowly desynchronize over time, where time here is just some other deterministic regular event. Right, so they end up determining unique and distinct pasts and futures. And they increasingly diverge with distance from now. Now, this is starting to get us close to these features of manifest time. So it's providing us some clues. It's giving us something that looks a bit like a past-future asymmetry and a privileged present, except it's not quite asymmetric, because when we look into the past, we can pinpoint all the clocks at the same time and look into the past, and we get the same entropy increasing behavior towards the past. And it doesn't really tell us anything about flow. So what we want to do, and this is what we're arguing, what we want to add is to model an agent as a learning machine. And here's our model. We're looking at this agent, first of all, as a causal agent, but we want to add features to this to make it a temporal agent. So this is an agent. It interacts with the world through sensors and actuators. It requires an entropy source to run, to put entropy into the system, sorry, to take entropy out of the system, technically, put energy into the system. Sensors and actuators dissipate heat. The learning machine, which we have a model for, also dissipates heat. Because this is thermodynamic, this particular causal agent gives us a causal perspective we want to add elements to this to give us a temporal perspective that's driven by the thermodynamic nature of the agent. And this is how we're going to add the temporal perspective. So I should say, first of all, the learning machine is just a noisy clock because it is thermodynamic in this sense with an embedded temporal perspective. And that's how we want to describe manifest time. It's a noisy clock, so it has these features about future to past asymmetry, but it's got an embedded temporal perspective as a thermodynamic engine. So it's able to tell us the past-future asymmetry. It's also able to tell us a privileged now, because that is the stored memory that it's got. We've got some problems with flow. I'll mention some of the problems with flow. So here's what we're going to do. This is Jim Hartle's IGES. He came up with this in 2005. If anybody knows, I've read that this is the first IGES, but I'm skeptical of that. Do people talk about IGESs before 2005? If you know, pop it in the chat. But what's going on here is, facing the other way, we've got a memory system. P0, P1, P2, P3 is a memory system. We've got an unconscious computation coming from the memory. We've got some schema for how the agent is processing this information. And then we've got conscious computation that gives us behavior that's spat out. So I should say IGES, information gathering and utilizing system. So we want to include memory in our causal agent to give us a temporal perspective, but it needs to be richer than what Hartle is giving us. So I know I'm very close to running out of time. So I'm just going to end with some more of Janan's thoughts on the structure of temporal perspectives. And we want to implement this. So Janan gives us a prescription for modeling a temporal perspective. Start with a system that is receiving perceptual input from the environment. So we can think of Hartle's IGES in this sense. Start with a system that is receiving perceptual input from the environment. Add a temporal dimension to its representational states. Allow memory to work recursively on those states. First storing them as snapshots of passing experiences, not just images of what was seen, but a full lived content of the experience with all the thoughts and feelings that were present, and then organizing them into an explicit autobiographical history whose contents are always being reconsidered and retrospectively modified. Now take a temporal cross-section of the resulting stream and you have the content of a temporally embedded perspective. And it is not just the events, but also the perspectives themselves that we represent. So there's going to be nested memories here. Later perspectives have earlier perspectives as constituents. Earlier ones have later ones as constituents. So in short, we're going to need a two-dimensional array to model the memory of a temporal perspective, an IGES with a temporal perspective. And that's our plan. All right, so this modeling quells the dual tendencies to either reify or reject features of temporal experience as illusory, right? Because this is an embedded physical system. It will have something like manifest time within it. But we're not saying that manifest time is somehow illusory. It is still real. It's still part of the physical system, but we don't need to either reject or reify the parts of the system. It's just a physical system. So they're actually implicit in the physical conception as the way time would appear from the perspective of a certain kind of embedded creature. So that's the plan of what we want to do. Now, ultimately, what would be really nice is to be able to explain all of the features of manifest time from the perspective, the temporal perspective of this embedded agent. But there's one big challenge, and I will finish with our big challenge. And our big challenge is, and it's a bit like the hard problem of consciousness, or getting space-time from something that's non-spatiotemporal. How on earth can we imagine the stimulus being presented to this agent if there is no objective temporal flow outside of the perspective of the agent? Now, I don't know how to solve that problem, but this is my hint for how we go about it. The beginning of a response is to argue that the thermodynamic arrow is also perspectival. And this is something that Ravelli has argued. All we know about thermodynamics is through the stimulus we receive from the world. So we want an agent to be able to receive that stimulus to model the world thermodynamically. I don't know how we square that circle, but it's an interesting challenge, and that's the challenge that I'm going to be looking at. So I will leave with a shameless plug of the first part of this project between Sally, Jared, and myself on causal agents. And I'm out of time. Thank you.
Thanks, Peter. That was awesome. In the next 2 minutes, does anyone have any questions?
Stop sharing.
Sam's got your hand up.
Yeah, I think this is just a quick question. Pete, you said that before what 10 to the -6 seconds or whatever it was, there were no clocks. But how do you, and then you link that to relational time, but how do you make sense of there being like time where there's no clocks if clocks are what give you time?
Yeah, I don't know. I find that an interesting question. So it's not necessarily that there's no clocks. It's that there's no structure that is able to act as a periodic limit cycle at that. Our best models of backwards in time cosmology. There's no structure in the universe that will be able to act as a limit cycle. I don't know what the answer to that is. I think that's really interesting. So, I mean, does it mean that we can't even say 10 to the -6 seconds is, after the Big Bang when we were already using the word after? I don't know what to say about that, but I think it's a really interesting conception of how relational time might affect these sorts of considerations in the cosmological model.
Yeah, cool. Thanks.
Okay, so I think we might move on. I think I'm up next. Let me show my screen. Good. So hi everyone. My name is Jules. I'm a second-year PhD student at the School of History and Philosophy of Science at the University of Sydney. I think I'm really excited because I think my talk really dovetails straight from what Pete was saying about flow, because this is sort of what I'm going to be talking about today, is precisely this question of how we might go about characterizing flow and cashing that out in terms of phenomena. Good. Okay. So good. So the plan for the talk is first and foremost just to quickly sketch out what we might mean when we refer to temporal flow, or what is often called in the philosophy of time literature temporal passage. From now on, I'll just be referring to it as flow. Then second, talking about what we might mean by phenomena. And for anyone who went to John Wilkins's talk, I imagine there'll be a fair bit of overlap there. Unfortunately, I didn't get to see it, but hopefully John can correct me on any glaring errors there. And then thirdly, looking at, if we take flow to be a kind of phenomena, what kind of phenomena would it be best characterized as? And then thirdly, sort of articulate the challenges. And again, similar to what Pete was saying, I won't be sort of providing a be-all and end-all solution, but rather trying to articulate in more precise terms, what is it that is stopping us from providing a more comprehensive characterization of flow? Good. So starting off with flow, it is notoriously difficult to get a grip on, both in physics and in philosophy. But we can say a few things about it nonetheless, that it should be distinguished from other standard temporal features. And one of the sort of lessons here is that we often call something time, but time really is just a bundle of different features that we tend to put under the umbrella. And so other features that flow should be distinguished from include things like duration, some preferred direction of time, or some privilege present. Of course, in different accounts of time, temporal flow would be correlated with some of these features, but conceptually, we can keep them distinct. Another thing we can say about flow is that it's one of the characteristic features of the so-called A series, as compared to the more quote-unquote static B series, big scare quotes there, where in the B series we just have before and after relations between events, and the A series has this more dynamic, flux-like quality to it, along with a privilege present and so on. But as you can see here already with my sort of hand waving and scare quotes, it's really difficult to provide either a positive definition, so a definition that's not sort of distinguishing it from other temporal features, or one that's free from any kind of metaphor of rivers or motion of some kind. And so, like I said at the beginning, one of the goals of this project is just trying to articulate the kinds of obstacles that are in place that inhibit us from providing a more comprehensive characterization of the flow. Good, so moving on to talking about phenomena. And this term phenomena has a very, very long history, and I'll be sort of brushing over most of it to just carve out two broad ways in which it's been understood in the past. The first of these you could call objective phenomena. So its emphasis is on external physical features of the world, and a handful of characteristics of such phenomena would be that they would be spatiotemporally individuated objects and events in the world, that they are explained in terms of laws or causal stories, and finally that they're given by some observation or measurement. And so these three criteria are given by Falkenberg, but similar things are said by Ian Hacking. And this sort of characterization of phenomena should be very familiar to scientists and physicists in particular, and has been the more dominant characterization in the philosophy of science of recent years. However, on the other hand, and the more how phenomena has been understood more throughout history is in hang on my slides. Yes, is in terms of features of experience. So what you might call subjective phenomena. And so this has a much more internalist emphasis. And the canonical system that cashes this out is this sort of Kantian framework. And again, a very brief sketch of what this Kantian framework is like is that we try to distinguish between noumena, which are the things in themselves that we don't have direct epistemic access to, as opposed to our appearances and then phenomena, where the appearances are said to be the undetermined objects of empirical intuition, and where those can be turned into phenomena when they are conceptually determined. And so phenomena require these a priori concepts to be able to be made intelligible. And very famously for our purposes here, such concepts were, in the Kantian framework, were spatial and temporal features themselves. Good. Sorry. And so we can sort of briefly sketch out a table of, in the columns, examples of processes that are said to be objective phenomena and not objective phenomena, and in the rows, similarly for subjective and non-subjective phenomena. And you can see in the top left, examples, very standard examples in science, where we have some story in the characterization of objective phenomena, but we could equally have a story to characterize it in terms of subjective phenomena. Whereas in the bottom left, we have phenomena which we have some objective characterization of, but no corresponding subjective characterization of, because it is sort of outside of our regime of experiences. So famously, relativistic effects and microscale quantum effects. And in the top right, we would have examples of phenomena which have no objective characterization, but have some subjective one, namely hallucinations. And in the bottom right, examples of neither. And so the question, or one way of posing the question would be, well, where does flow lie in this grid? And for the purpose of this discussion, I will be taking for granted that we have an experience as of flow. There's been a few arguments arguing for the fact that we actually don't have such an experience of flow, but instead we mistakenly believe that we have such an experience. I'll be sort of putting that aside for the time being and taking for granted that we do in fact have such an experience of flow. And so my claim is that it's somewhere in these two cells here. That is not to say that there won't be interesting things, there won't be challenges when trying to characterize it as subjective phenomena, but we'll also be trying to do so for the objective case. Good, and so we can start thinking about how we might go about characterizing flow as such an objective phenomena, and thinking about the criteria that we saw previously. We can look at these first two examples, and my claim is that these two seem to be rather plausible for temporal flow. And this is despite the fact that they're not found, or it's sort of very difficult to find temporal flow in our standard physical theories, as Peter was mentioning in the previous talk. However, this is not to say that our physical theories rule out temporal flow. So I think this is sort of similar to presentist, picture which Patrick will be defending, where it's broadly agreed that our physical theories aren't in favor of presentism or temporal flow. However, it's still a live option. And not only that, you have more speculative programs like causal set theory, which Sam will be talking about later in this session, which some people have argued that flow might be found in such a description. And so the first two references there are talking about causal set theory in general and defending it. And the latter two are references where the authors try to articulate how some notion of objective flow might be found in such a theory. Good, and so next up we have the empirical criteria for objective phenomena. And my claim is that this is much trickier to try and find. Because on the one hand, a very naive reading of observation might lead one to say, well, look, I have plenty of observational evidence for temporal flow. My everyday experience, I experience temporal flow every conscious moment, and so shouldn't that be plenty of observational experience? But the problem with this is that this isn't the kind of publicly accessible intersubjective observations that science and physics cares about. And so this leads us to what is a big part of the literature on objective phenomena, which is the relationship between data and phenomena. And so a couple of the main texts on this. And so just a quick primer on this notion. In this picture, we have phenomena which are the underlying objective features of some physical theory. And the data are meant to pick out very specific features of the phenomena in some not obvious ways. And so some canonical examples, both from GR. So we have gravitational waves here, which is, so you might have some abstract representation of what gravitational waves look like. And then the corresponding data for that phenomena would be the LIGO signals. And a more historical example, but again from GR, is light, gravitational bending of light. And corresponding data here are the plates from Eddington's expedition looking at the eclipse. And so one of the main take-homes from this literature on connecting data and phenomena is characterized by this quote from Woodward, where he says that fundamental theories like GR fail to provide such explanations of data, which is maybe sort of unintuitive. And I think, well, what is it that fundamental theories are trying to do, if not explain some kind of data? But he says that in part because data commonly reflect the causal influences of many different factors besides those that fall within the purview of any single general theory. And so I think the LIGO case is a perfect example of where, to make sense of these signals, it's not enough just to have a GR textbook in front of you. You need to be acutely aware of the sort of contingent experimental conditions that brought about this kind of data. And so I think, going back to clocks, and a risk of sort of going over not too much of Peter's discussion, I think there's two things to learn from this discussion. Well, there's two ways in which we can approach the empirical basis of flow. Either we can look at the classic physicist adage of time is whatever a clock measures, and try and think carefully about the kinds of physical processes that bring about clocks and how we might be able to extract some relevant data from a potentially underlying phenomena of flow. And I think, as Peter points out, this is very different from the usual, physicist idealization of simple clocks. Whereas, on the other hand, we can shift focus and try and look at the capacities of brains, since our main motivations for trying to find some objective phenomena of flow is our subjective experience. One might think that our brain has some capacity that is tracking some objective feature of the world, and by doing neuroscience, we might be able to find such a capacity. But good, but the lesson here is that both of these approaches are still very much open questions. And I think this is one of the big hurdles in providing such a characterization of objective flow. So now moving on to flow as a subjective phenomena. Now, as I previously stated, you can sort of think of subjective phenomena in this sort of Kantian stance. And like I said, the relevant feature of this Kantian stance is that spatial and temporal features themselves are understood to be these conceptual categories. And there's this nice paper by Sample where she looks at how one might fit in the sort of standard philosophy of time A and B series into this Kantian framework, and she concludes that, well, A series could be described, appearances can be described as an A series, while the phenomena are understood as a B series. And good, that's sort of all well and good, but as probably most of you are thinking right now, why should I care? I'm not a Kantian, right? So what can I take away from this? And I think there's one of the key morals from, even if you don't fully sort of buy into this Kantian framework, which there's sort of many reasons why you might not be, you might not want to think that space is sort of just all in the head and that it doesn't have some sort of mind-independent basis. And so I claim that one of the main morals of this Kantian stance is that there are no ready-made phenomena. That and it's sort of expressed nicely in this quote by Massimi, where she says, "There are no ready-made phenomena as observable or perceivable objects in nature. In a way, we have to make them. And once we make them, we have to prove them right. Namely, we have to demonstrate that what we have inserted into the appearances for the sake of possible experience is truly there. And so there's this focus on the kinds of conceptual, the kind of conceptual machinery that we bring to bear in our scientific understanding of nature. And again, just another quote from that same paper, she says, "We can gain scientific knowledge of nature only by making appearances conform to our way of representing, rather than trying hard to make our hypotheses conform to nature." And I think this attitude, even if you don't subscribe to the Kantian system, is one that we can take with us when trying to understand subjective phenomena and foregrounding the kinds of conceptual resources that we bring to bear in constructing phenomena. And just to give more context, Massimi here is talking about the historical example of Galileo's mathematization of nature in this case. And I think this quote from Ismail is from a recent chapter where I think it highlights that time is often seen as the troubled sibling of space, where space is seen as the more sort of tractable, philosophically tractable concept for philosophers of science to get a grip on, especially in connecting it up to our phenomenology. But in this chapter, Ismail talks about, this is in the context of quantum gravity, where there might be a fundamentally non-spatiotemporal description and how we might recover our phenomenology of space. She says this, she says, "There is no question that we have an immediate awareness of the visible and tangible reality of space. But what that awareness amounts to, and whether it supports the requirement that space has to be recovered as a concrete external structure, is not something that has received enough attention." And so my claim is that I think you can replace space here with flow, and it's also exactly right. That we have some immediate awareness of the reality of temporal flow, but what that awareness amounts to is still not clear. And whether or not that awareness has to be recovered as some concrete external structure or as a product of the kind of conceptual categories that we use to understand nature is still an open question. And so I guess just to sort of start wrapping up, I think why temporal flow is such an elusive concept to get a grip on is that it uses, or to be able to fully characterize it, you need to take into account all these different fields. And so I think I think that's why it makes it a difficult problem, but I think it also makes it a fruitful one, particularly for HBS style folks who are sort of inherently interdisciplinary. And so some final take-home messages. So again, I think the goal here was to just try and articulate how we might go about characterizing temporal flow in terms of phenomena. And I think in that process, you come up against different, but I think ultimately related obstacles. And I think something we can learn from both of the objective and subjective approaches is that unlike more standard temporal features, flow doesn't have the luxury of drawing upon the conceptual resources of our standard and orthodox physical theories to be able to fully account for it. And that I think talk of phenomena highlights the relevant connections between metaphysics and epistemology. And I think I really like Peter's point on this, that a lot of focus has been on some underlying metaphysics of relativity or so on, but I think drawing that connection between the metaphysics and the epistemology here is the right approach. And that because of this, you can't escape discussions of realism when grappling with more controversial phenomena. And those are some of the references. Thank you very much. Anyone have any questions? Brittany?
Yes, hello. This might be a silly one, but at the beginning you talked about how flow is sort of a dangerous term to use because of the metaphorical associations. And I wondered what made you end up choosing to use flow for your discussion over, I think you called it passage. So what made it flow a better option there?
Yeah, good question. I mean, I don't have a very satisfying answer other than it's sort of short and I think it's more evocative to people who aren't necessarily up to date on the philosophy of time way of speaking about things. But other than that, not really much other reason. So I have other hands up. John Wilkins.
Right. Thanks very much, Jules. It was a very interesting talk. And, as you know, I've got a serious interest in the relationship between data and phenomena and so forth. But it seems to me that there's a bit of an equivocation in using the term phenomena when you're talking about the causal structures or the theoretical structures that are representing causal structures underlying it. Wouldn't that be what Kant called noumena?
What would Kant call noumena? What would Kant call noumena?
What you're calling objective phenomena. See, the Wogan-Woodward view, as I understand it, is that you find patterns in data that are repeatable and regular and call for explanation or have been previously explained. And so they're phenomena, right? There's a sort of cognitive epistemic aspect to phenomena. Now, I know that in science, there's an equivocation between noumena and phenomena because not all scientists have read their Kant. But it just seems to me that it's confusing to call these things phenomena.
So I think the way I understand it is that there's a certain feedback loop, right? Because you're right that you sort of start off with patterns of data and you use those patterns of data to formulate some theoretical framework which posits some underlying phenomena. But all you have epistemic access to is those patterns of data. And so, whereas I think the Kant's noumena, there's more of there's sort of less epistemic access to it than in the sort of more objective phenomena characterization of it. But you're right that it's a very tricky problem, and the distinctions that I'm making are arguably very artificial, and that there's connections to be made.
Yeah. Okay. Thank you.
Thank you, John.
It's my name there, but it's Adrian Flitney here who's got the question.
So I'm unashamedly a physicist and not a philosopher, and so I'm wondering about this role of both special and general relativity, which sort of says that intervals of time depend upon the observer. The interval of time between two events depend upon the observer, and how this, if we're going to have some conception of flow of time, then it's going to have to be observer dependent.
Yeah, absolutely. And so I think that's exactly right. And I think that, again, sort of dovetails into what Peter was saying about being very careful about not reifying necessarily global laws and paying attention to the way agents are embedded in, say, a space-time manifold. And you're absolutely right that when doing that, you absolutely get proper time depending on comparing proper time of different world lines, different and all these sorts of things. So you're absolutely right that notions of duration and to be able to recover our subjective experiences of duration and more speculatively flow, we have to take into account these general relativistic effects.
Yeah, I went the special relativistic effects as well, but yeah, both.
Good. No other questions? So then I think we can move on. So I think next up is Patrick. I'll just give a quick blurb. So Patrick is a final year PhD candidate at the University of Sydney. His PhD work, along with today's presentation, is on how our best physics, in particular quantum mechanics, might be understood and interpreted within an a-theoretic understanding of time, such as within presentism. One of the main consequences of this perspective is that both the future and the past can be thought of as open, in the sense that one can only describe what has and will happen in terms of a range of probabilities. So I'll throw it to you, Patrick.
Great, thank you for that, Jules. Can everybody hear me clearly? I've had issues with this computer before. All right, well, just let me know if there's any problems. So I don't have any slides for this talk. I'm actually quite looking forward to the prospect of delivering a talk to kind of electronic recreation of a room full of people. I can see all your faces, which is quite nice. And I imagine many of us have spent the last 2 years delivering lectures and tutorials to our own slides. So I'm quite glad not to have that filling up my entire screen or yours. But I hope everything can manage to remain clear. It is a short and not too complicated talk, so hopefully that all works. So today I'm going to be talking about presentism and more broadly kind of, I guess, traditional dynamic A theories, theories that posit that, the certain features of experiential time that Jules was just talking about, features like an objective present, a flow of time, these sorts of things, are sort of real features of the world that are kind of out there. And particularly I'm going to be talking about that in relation to non-relativistic quantum mechanics. And this focus of mine might seem to those in the know as, I guess, a little bit old school. I mean, why talk about quantum mechanics when, a lot of people have moved on to talking about much more exciting, speculative frontier ideas in quantum gravity? And likewise, why talk about the A theories when, it seems like the theories of relativity kind of discount those, or at least seriously favor other kinds of theories where there's just sort of space-time and there's no objective present and these sorts of things. Now, look, it would be remiss of me not to say that there are at least some defenses of A theories in response to relativity theory. And actually, 2 years ago at this conference, when it was in person, I gave a talk on that particular topic, but that won't be a huge focus today. Instead, I will largely take it as a given that relativity theory at least sort of strongly favors other sorts of kind of four-dimensional space-time views. But I suppose something that I want to emphasize here is that until such a time as, we have a kind of popular kind of central theory of quantum gravity, as long as theories of quantum gravity remain kind of frontier and speculative, there is something to be said for the fact that the best physics that we have that's kind of more established is special and general relativity on the one hand, and non-relativistic quantum mechanics on the other hand. It's already pretty well understood that the pictures of time that these theories give to us are pretty different. Obviously, within relativity theory, we have this kind of space-time framework where there's no objective simultaneity. There certainly doesn't seem to be much notion of passage or any kind of objective present or anything like this. Whereas in quantum mechanics, there are at least some sort of quirks that seem hard to place within that kind of framework. Issues like non-locality and the questions that raises for time. Time kind of irreversible or asymmetric kind of processes, the fact that measurement, for instance, features in that way, and the kind of asymmetric things that arise out of thermodynamics and those sorts of problems. So there certainly is already a kind of disagreement out there between the kind of two big branches of physics that exist at the moment. But in my experience, I suppose, interacting with physicists myself, it seems like it is often taken as a kind of a given that it's relativity theory, special and general relativity theory, really, that put forward a kind of ontology of time, that sort of support a particular view about exactly how time is, that there is kind of a space-time, relativistic space-time, and that's kind of what the theories of relativity are telling us. Whereas the impression that at least I get is that people sort of look at quantum mechanics and think, oh, well, quantum mechanics kind of introduces a few quirks into this idea. It's a little difficult to deal with. And sort of one day when we kind of theorize about quantum gravity, we may have to change up our idea of time to being something that isn't quite what relativity theory tells us. But that I think there is a sort of treatment of quantum mechanics as not actually supporting, clearly any particular ontology of time itself. So that, until such a time as we get an update from quantum gravity, our kind of running theory, our sort of working idea is probably that we live in kind of relativistic space-time, pending some kind of quirks as to how that's going to be rectified with what comes out of quantum mechanics. And I think there's a sort of indications of that come out of what we've just heard from Peter and Jules as well, right? So from Jules, you mentioned that when people think of what physics tells us about time, the natural things to run towards are relativistic space-time, general relativity, these kind of manifolds of space-time that we get from that kind of branch. And likewise, from you, Peter, there was a discussion here about the kind of focus on time in physics has been very much on relativity theory. What does relativity theory tell us about time? But I suppose what's interesting about this is that at least some of the kind of quirks that seem to exist within non-relativistic quantum mechanics seem to be in some sense distinctly atheoretical. They point to things like absolute simultaneity, which is something that atheorists are very much more in favor of, and which doesn't sit nearly as sweetly with what we get from sort of eternalism or from these kind of four-dimensional views that special and general relativity are all about. And I guess a question I've got in my mind is, how far does this kind of similarity with A theory go? Should we perhaps be thinking that quantum mechanics does just introduce a few kind of odd quirks that need to be dealt with? Or is it the case that quantum mechanics could be shown to properly kind of work a lot better with some views and work less well with other views? Because I can certainly see it being a different kind of environment if people were under the impression that the theories of relativity favored one particular sort of ontology, but the theories of quantum mechanics or non-relativistic quantum mechanics actually favored some kind of other definable ontology, as opposed to just introducing some odd quirks into the kind of picture of time that we have. Now, obviously, that will be a kind of huge project to sort of properly establish what quantum theory would tell us about time, and there have already been at least certainly some investigations into what quantum theory tells us about time. But I guess the reason that I want to talk about the A theories and non-relativistic quantum mechanics is because I think there's sort of value in investigating, well, what picture of time does non-relativistic quantum mechanics paint? And is that, substantially different from the kind of picture that relativity paints? Should it be the case that we sort of think about the world as being probably like relativity, pending updates and changes from quantum gravity? Or should we be thinking about it in a different sort of way from that? So a common strategy for approaching these sorts of problems, and I think a strategy that we've seen already come out from this talks we've had so far, is to kind of start from the physics and start from saying, look, let's make clear as to what it is that the physics establishes, what we know from our best physics, and then try and see what kind of emerges from that and how that might kind of produce something that maybe resembles the experiential time that we have, or resembles these sorts of features like an absolute present or the passage of time, or the kind of features that I'm interested in talking about. My approach is going to be a little bit different here, which is that I think that particularly because there are still some sort of open problems and quirks in quantum mechanics, problems like how do we interpret quantum mechanics, which make it at times a bit difficult to say cleanly that certain things are just established as a result of quantum theory, and we can work from those to try and see what time looks like. Instead, I think my approach to this problem, and obviously both approaches can have some value, but my approach to this problem is to sort of say, look, if we just assume that the world works in some kind of atheoretic sense, if we assume that there is an absolute present, or if we assume that the passage of time is kind of out there in the world in at least some sense, how does that affect the way that we think about quantum mechanics? How does that affect, for instance, the way that we interpret quantum mechanics, or the way that we deal with problems in quantum mechanics? And perhaps it doesn't do much. Perhaps we assume presentism and the problems are much as the problems already were, in which case the strategy hasn't really done anything and hasn't achieved much. Or alternatively, and what I'm going to argue is at least plausible, is that if you approach problems in quantum mechanics, like how to interpret quantum mechanics, from a kind of atheoretic perspective, then some of those problems might be easier to solve, or there might be new and interesting ways in which to solve them, which would seem to indicate that there is at least a kind of path to go down to say, look, here is a kind of a-theoretic view of the world which works really well with quantum mechanics and perhaps avoids some of the problems that we otherwise face within quantum mechanics. Obviously, this is pretty kind of speculative or exploratory stuff. I'm not today going to articulate what that kind of great kind of a-theoretic view of quantum mechanics is going to be. But what I want to do is, I guess, give an indication of a few examples of where a-theories or passage or an objective present or these sorts of ideas could provide an interesting kind of perspective on things that are otherwise kind of thorny problems in terms of how quantum mechanics is understood and interpreted and some of the problems that come up in it. So that's going to be what I do through the rest of this talk, is just give a few examples of areas where a-theories and these sorts of ideas could be kind of put to some use in terms of trying to understand quantum mechanics in new, interesting, and maybe good ways. Now, the first one to talk about, and probably the most obvious one to talk about, is non-locality and simultaneity. So obviously within quantum mechanics for a long time, there have been debates going on about what sorts of non-local interactions could occur in things like the EPR style kind of paradoxes. And for those in the audience who are less acquainted with them, though I assume quite a few of us are acquainted with them, the idea here is you can take a couple of particles, for instance, and make them interact in a way that causes them to become entangled, and then when you sort of perform certain actions like measurement on one of those particles, it seems like at least something happens to the other particle instantaneously or immediately or simultaneously. And then there's a debate from there about what exactly is it that is going on, right? So I think it's pretty reasonably well established that you can't use this to communicate information. It doesn't necessarily transfer energy, though at times there's been a little bit of debate about that. But that doesn't stop it from being the case that at the very least it seems like something non-local happens. There are debates about this. I don't want to get really into the details about the different ways that you can interpret quantum mechanics to try and get around this. But certainly it at least seems as if there is some sort of non-local interaction that occurs, even if that non-local interaction is not information or energy communicating. And if that's so, if we're resigned to the fact that that's going to happen, then that has implications to how we understand time, because if there is something non-local that occurs between A and B, then that seems to indicate that there is at least some sensible notion of what it means for A and B to be simultaneous with one another, or for something to happen to them together, despite the fact that they are separated across space. And so the question becomes, how do we make sense of that within the picture of time that we have? Now, if you approach this problem from, I guess, a kind of four-dimensionalist, eternalist perspective, if you take it that there exists the past, future, present all together within space-time, then a natural way of approaching this problem, which is not, I suppose, a quantum gravity-esque kind of more speculative way of approaching this problem, but a natural way of approaching this problem is to kind of just cut up your four-dimensional space-time into a whole bunch of slices, to say that there's basically simultaneity that exists in your four-dimensional world. And I would put it out there that that's at least seems to be kind of the thing that is sort of most anathema, the most oppositional to the kind of worldview that we get from relativity. Obviously, many people take it that kind of the whole point of what relativity theory tells us is that you don't cut up the four-dimensional world into a series of kind of objective three-dimensional slices. And so hence, we get problems in terms of the quantum mechanical picture of time disagreeing, it seems pretty clearly with the picture of time that we get from relativity theory. What I want to point out here is that there are ways of approaching this problem from a kind of a-theoretic perspective that at least understand simultaneity in a bit of a different way. That doesn't mean it's a way that's going to agree totally with relativistic theory, but there are further tools that can potentially be introduced from this. And one of those tools, which has been, I've explored in previous work and also kind of shows up from time to time in a few theories that people put forward, is that you could have an A-theory where there is an absolute present, and by definition, everything that is absolutely present is simultaneous with everything else, perhaps. But that otherwise, outside of the present, in the past and the future, you have a structure of space-time that is not necessarily sliced up into a whole bunch of these slices in the way that you might otherwise characterize it to be. I think this is probably easiest to understand in the context of the growing block theory. So you could have, for instance, a growing block world, which is a four-dimensional world that ends at a kind of edge. So there's a past, there's an edge, and that edge kind of grows, and you get this kind of growing universe over time where past and present exist, but the future does not. But within that worldview, it is at least plausible that somebody could argue for a growing block world where once the block is grown, once you look at things in the body of the block, those things are not kind of cut up into a series of sort of physical slices, that the block itself resembles the block of four-dimensional space-time once it has grown. So all you're proposing for this growing block world is that that you have a four-dimensional world that just ends at a certain edge. And that's a bit of a different conception of absolute presentness or simultaneity from just cutting up a four-dimensional world. In that kind of world, you can say, look, there is some kind of notion of what it means for non-local interaction to occur, which is that you have two things that are both on the edge at the same time, and you have some sort of processes which make everything or pairs of things on the edge behave differently or act in a certain way. But you don't have, I suppose, a kind of broader, generalized notion of simultaneity surfaces that you might otherwise have in a kind of sliced up universe. And there are ways of arguing, and I do this in other work, I'm not going to get into this in a whole lot of detail here, but it may be possible to argue that a world like this one is one that doesn't clash so clearly with relativity theory. Perhaps it's one in which we can't observe simultaneity, since our observations are kind of, by the time we observe things, they are past things, and things out there in the past aren't cut up into slices. But it's nonetheless one where non-local interactions can, in some sense, be made sense of. So this is kind of an illustration of a way in which, by approaching this problem from an a-theoretic perspective, there are at least could be more tools for trying to understand non-locality, perhaps tools that work in a way that is good or a way that is useful. Obviously, this is somewhat of a revisionary way of understanding a-theories. Traditionally, the growing block theory, for instance, is understood as a theory that's all about slices. It's about a whole lot of slices and new slices coming into existence with every moment, and the past is supposed to be sliced too. But there are potentially ways of investigating growing block theories that are not so committed to this idea, that the whole of the past is sliced up in that way. So that's one example of where approaching quantum mechanics from an a-theoretic perspective could lead to kind of interesting consequences. Here's a second one, a second example that I want to talk about in terms of how this could work. And my second example relates to time asymmetry or time reversal. So obviously, there's a kind of well-understood problem, not just in quantum mechanics, but in thermodynamics as well, about the problem we have with sort of time asymmetric processes emerging on a kind of macroscopic level, or popping up from time to time in places like measurement, even though the micro-scale physics that we describe the world in terms of is often described as time symmetric. And there are various solutions to these problems, solutions like the kind of early and late stages of the universe having certain boundary conditions for entropy and that sort of thing. But there's at least this kind of open question and problem as to how do we account for time symmetric or asymmetric processes, particularly time asymmetric processes arising out of fundamental processes that are time symmetric. For the sake of this discussion, I might keep it to sort of a simpler kind of thermodynamic example, because the argument I will put forward works for that, but there are examples that come through in quantum mechanics that this is relevant to too. So an obvious example of this is, if you've got an oven full of hot gas and you open it, all the hot gas rushes out and, reaches equilibrium with the room that you're in. And this is a kind of process that we would expect to happen even under time reversal. If we reversed time and all the gas particles, the kind of, the billiard balls in the oven reversed direction, then we would still expect under time reversal that if you opened an oven, all the hot gas would flow out and mix with the room. But this is pretty weird because obviously we do not see the time reversed opening hot gas situation, because what that would look like, it seems, would be a kind of situation where I walk up to an oven, I open it, and sort of hot gas coalesces out of the air into the oven as I kind of shut the door, which is sort of the time reversed version of opening an oven full of hot gas. But obviously we never see that occur. And this is a bit of a problem if you subscribe to, I guess, a kind of a position where time is understood to be a dimension. And part of the reason it's a problem is because if time is a kind of dimension along which you can go kind of forwards or backwards, then there is a very clear and physical meaning behind the notion of time reversal. To say that, opening an oven full of hot gas under time reversal is something we expect to occur, just is to say that we expect, hot gas to coalesce into ovens when time goes forward. When you talk about time reversed processes, that has a kind of very physical meaning in the actual world. Whereas it is possible, at least within A theories, particularly presentism, where you don't conceive of time as existing in the form of a dimension, to understand time reversal in a different and potentially less problematic way. So there's a bit of, obviously there is a discussion and a debate about how exactly presentists should understand time, the passage of time, change, and these sorts of things. But certainly it seems at least kind of only within presentism, or at least only within a view like this one where time is not understood to exist in the form of a dimension, it may be possible to construe time as not being intrinsically directional, that time doesn't necessarily pass in that way as opposed to that way, but rather you exist in, there's just a kind of three-dimensional world full of three-dimensional objects, and the passage of time is just a kind of primitive sense or whatever in which those things all just change. And they don't change in a way that's intrinsically forwards or backwards. We might sort of extrapolate from those changes kind of representations of what's happened in the past, which are directional themselves. But the objects themselves are kind of just changing. They're not changing in a way that's kind of forwards as opposed to backwards or something like that. And there is at least a case to be made for this. Obviously, that's, there are plenty of presentist notions where that wouldn't be the case. But there is room within presentism to make that kind of argument, where there is not so much room within other theories where time is treated as a dimension. And in that instance, if you don't treat time as directional or a dimension, then that casts a totally different light on how you understand time asymmetry or symmetry, or time reversal or irreversibility. Because it doesn't really make sense now to ask a question like, what would happen if time goes backwards? Because time isn't going forwards in the first place. Time is just passing. The best that you can do in that sort of situation is you can say, well, what would happen in some alternative possible world if the laws of nature were kind of similar to how they are now, but some of the signs were changed around. The plus signs were changed for minus signs, and the minus signs were changed for plus signs, or something like that. What would happen in that kind of alternative possible world where the passage of time works in a sort of opposite kind of a way? But crucially, a presentist wouldn't be committed to any particular belief about what would happen in a possible world like that, because at this point we're just speculating about some possible world that is not the actual world. It is a world where the laws of nature just kind of work a bit differently. So it is at least plausible that a presentist could say, well, look, yeah, maybe if you change the laws around and replace some minus signs with plus signs or whatever, then you would see some interesting things. You would see some things going backwards, but other things wouldn't. You'd still get hot gas coming out of ovens, even though the billiard balls are all going in the opposite direction. Measurement perhaps wouldn't run in a reversed way, even though the laws have been reversed or something like that. So you could have a situation where time reversal doesn't reverse everything, right? Where you have some things that are kind of asymmetric and some things that are symmetric under it. But in a way, none of that matters that much if you don't hold that time is directional, because all of this is just speculation about some possible world where it's opposites day and the laws are a bit different. But none of that has a direct and obvious physical bearing on what goes on in the actual world, because in the actual world, time isn't going backwards, or it isn't opposites day. Time just runs the way that it runs. So this is another example, I think, of where approaching these sorts of problems from an atheoretic perspective can at least offer new tools or new ideas that might not otherwise be accessible within positions on time that are not atheoretic. So I'm out of time here, so I think I better wrap up. But I guess the conclusion here is not a particularly firm one. I don't mean to claim here that the A theories are proved true by quantum mechanics, or that that is the only way to understand quantum mechanics. But I think there is at least an interesting question to be asked here about how kind of dynamic, how atheoretical we should construe quantum mechanics to be. Quantum mechanics certainly seems to present a vision of time that is different from the kind of four-dimensional relativistic picture of time. And the question is how different? And I think there are at least some interesting ways in which approaching quantum mechanics from this kind of atheoretic perspective can raise some interesting responses to problems, or allow for us to think about some of the quirks of quantum mechanics in new and interesting ways, which could at least be explored in more detail. So that's the talk. I hope you enjoyed it. Happy for questions.
Thanks so much, Patrick. I guess I'll start us off and leave people time to think of questions. But sure. In your discussion about time reversal, you sort of frame it as, well, look, in the standard B theory picture, time reversal is sort of seen as this uncontroversial thing, whereas it's more difficult to characterize in a more A theory sense. But I think, and Brian Roberts has talked about this, even in a B theory sense, there's sort of tricky sort of problems about what we mean when we talk about time reversal, in that unlike other space-time symmetries like time translation, there's no clear way to how to operationalize that, right? In spatial symmetries, you take a system and you move it, right? And that somehow operationalizes what we mean by spatial symmetry, but you can't take a timeline and sort of swap it over, right? And so I think I'm arguing in favor of your project here, is in that you're saying, well, it might be difficult to characterize time translation in A theory. It's like, well, there's still challenges in a B theoretic sense as well.
Yeah, sure. No, that is an interesting point. And I think it's not lost on me that, during my master's, I was working with a bunch of theoretical physicists, some of whom were quite interested in working on the kind of CPT violation, which part of it is asking, is there time reversal symmetry or time reversal asymmetry? But in practice, what they're looking at is they're looking at differences between the behavior of particles and their corresponding antiparticles. And I think there's a lot to be said here for the fact that what they are learning is they are learning about how particles and antiparticles differ. And only by some assumptions, which certainly you could challenge, are they learning about what time reversal does. Because as you say, you can't really directly test what time reversal does because you can't grab the crank and turn it the other way. So I think you're right that there are interesting questions to be asked about how we understand time reversal even within the B theory, and whether the assumptions we make about time reversal in relation to particles and antiparticles, for instance, are reasonable ones to be making.
Sam Barron has your hand up.
Yeah, I was just wondering, Patrick, whether you think that the extent to which the A theory is useful depends on the interpretation of quantum mechanics that you're interested in. I suspect that for some theories, there's some interpretations, it's going to be, the A theory might be useful and some it might not, but maybe I'm wrong about that. I just wondered if you had any thoughts.
Yeah, so no, I absolutely do, and I agree. I think it probably would be more useful within some interpretations than others. One other point that I didn't really have time to get to here in terms of ways that the A theory can be useful is that that you can sort of understand, this probably would take too long to get into, but I think that there is a sense in which A theories and sort of intuitive or our experiential understanding of time describes at least the path, at least the future, and under some theories even the past, as kind of open or undetermined or kind of probabilistic or these sorts of things. And there's a question as to whether or not that could be incorporated into the way that we understand quantum systems, given that we understand quantum systems in a way that's kind of probabilistic, kind of open, these sorts of wave functions that exist, and these sort of odd quirks that arise, during measurement and these sorts of things. So we suddenly transfer from talking about systems as being kind of probabilistic to talking about them as having certain particular states. But I think from my own investigations that I've done into that, I think, yeah, it would depend a lot on your interpretation of quantum mechanics as to how far that could be used or how useful that could be. So yeah, no, I think you're right that I think it would probably depend on your interpretation of quantum mechanics. But then there's just a lot to talk about there, right? There's a lot of interpretations of quantum mechanics and a lot of ways in which A theories could be applied to them. So I think you're almost certainly correct about that.
Someone in John Bigelow's camera has a question.
Yes, I'm just wanting to put my particle physics hat on.
Yeah, right.
Work in quantum field theory. So we've got charge parity and time
symmetry.
Yeah. But you've asked both parity and time reversal symmetries are violated. So in a sense, there's some symmetry, if I can use that term, that space and time are similar in the sense of, if I reflect everything in a mirror, I violate parity symmetry. And if I sort of reflect everything in inverted commas in a time mirror, I violate time reversal symmetry. That's sort of just a comment rather than a question, but I mean, I'm happy if you want to develop on that. So.
Yeah, well, again, it's I guess it's interesting because if you do subscribe to a kind of A theoretic perspective, which I talk about, but which has not, I don't think has been looked at in great detail before, where time doesn't really have a direction, then there's a lot more freedom to just say, well, things just are as they are. And if you try and hold up a mirror to, a temporal mirror to the laws, then you can sort of mess with the laws in any way you want to, but it doesn't really have that much bearing on how things actually exist. So there's plenty of room in that, I suppose, for time reversal symmetry and asymmetry to kind of, and violations of time reversal symmetry to pop out. Whereas, yeah, I think, I don't know, I mean, as I mentioned before, I guess a lot of these tests ultimately boil down to testing the kind of distinctions between particle and antiparticle behavior. And I feel like it's what assumptions you make from there about what it's telling us about the underlying nature of time. They're tricky to deal with, but admittedly, it's not a field that I work in anymore particularly much. I went to the dark side and started doing metaphysics instead of continuing with particle physics. But I think, yeah, obviously you'd want to kind of, if you were going to try and outline a more detailed view about what a sort of atheoretic quantum mechanics would look like, you'd want to get into those sorts of details, absolutely.
Maybe one final quick question from Peter.
I'll make it very quick, Patrick. It's a suggestion to go and have a look at something. There are a series of new no-go theorems in the last 3 years. With the extended Wigner's friend scenario. If you've heard of them, one of them comes out of Griffith University. It's probably the most advanced one, so up here in Queensland. That pretty much rules out categorically an observer independent block. It is probably one of the most interesting results since Bell's theorem, and you might be interested in that considering your project.
It rules out an observer-independent what, sorry?
Block.
Block. Ah, interesting.
There can be no third-person, absolute, God's eye view description of reality in quantum mechanics, is what it tells us.
Ah, interesting.
You might find that interesting.
Yeah, I think I would find it interesting. I'm not much of a blockhead myself. I generally defend presentism, so that I, wouldn't mind if some of those things came out. But yeah, no, that is really interesting. So I'll look into it.
Fantastic. All right. So last up, we have Sam. And so Sam Barron is an associate professor of philosophy at the Australian Catholic University. He works primarily in the metaphysics of science, focusing on the nature of time and the existence of mathematical objects. Sam will be presenting work examining recent developments in the fundamental physics to advocate a causal theory of time. While causal theories of time have received philosophical pushback in the past, these new developments from quantum gravity provide good reason to re-examine this approach, of which Sam provides a defense. So yes, and Sam has a handout in the chat. If anyone wants to take a look, and I'll leave it to you, Sam.
Cool. Thanks, Jules, and thanks for organizing this session. I actually had cut what I'm about to tell you about out of the handout. But I thought I'd put it back in because Pete gave us history of time. So I thought I'd give us another sort of terrible history of time as well. This time it's a history of the causal theory of time. This one's also massively incomplete, but it does sort of interact with some of the historical points that Pete was picking up on. So it sort of begins in arguably 1716 with Leibniz, who gives us an account of temporal succession in terms of causal explanation. This is the start of the relational theory of time, but also the causal theory of time. So, Leibniz was both, but you don't have to be a causal theorist in order to be a relationist. And so the relationism breaks off later on. Then Kant builds on Leibniz's account in order to give us an analysis of both simultaneity and succession in causal terms. Then you get this theory being kicked around for a bit. Schopenhauer gets into the act and sort of gets annoyed by Kant's account, but I'm yet to fully work out what his objections were. You get Leclerc coming back in 1896, and actually Leclerc is the one that coins the name the causal theory of time. And then, as Pete said, Einstein developed special relativity and general relativity in 05 and 16. In 1914, Robb and then Carnap in 1925, they provide axiomatic versions of special relativity in which temporal order is analyzed as causal order. So they actually give you these sort of causal relativistic views. Then Reichenbach gives you general relativity in causal terms. And that's followed by Grunbaum, who gives you a version of Reichenbach's account in 63, which irons out some of the difficulties. One of the things that Grunbaum does is actually uses a symmetrical causal relation as the fundamental notion of causation in the theory. Then you get philosophers coming in and criticizing it pretty heavily. So Lacey and Smart, they criticize the causal theory of time, and some of their objections I'll be thinking about. And then Van Fraassen comes in and defends Grunbaum's view in 1970. In his book, in his introduction to the philosophy of space and time book, there's a lot of that book that's not introductory at all. And in particular, there's a chapter defending a causal theory of space-time and defending Grunbaum's view. And then philosophical interest in the theory wanes. But what happens in 76 and 77 is you get Stephen Hawking and David Mullerman proving these theorems about the relationship between space-time and causal structure. In particular, that space-times and sort of causal structures are isomorphic in some respects. And in particular, the kind of the light cone structure of a space-time is a causal structure. And it turns out that you can get a lot of the other structure back in general relativity by using that causal structure. And that causal structure is a sort of partial order, more or less. Then in the 90s and 2000s, these theorems by Hawking and Mullerman get developed by Faye Dowker, Sorkin and Ridout to develop an approach to quantum gravity. I don't want to call it a theory of quantum gravity. It's very much a sort of suggestion of how we might go. What they do is they start with a kind of discrete causal structure, and then use that to try and recover some of the metric features of general relativity. So what's interesting, I think, about this little story is that philosophers sort of lose interest in the 70s, and then, but physicists don't. There's a continued project in physics, and I think that philosophy should come back and take another look at the causal theory of space-time, and that's what I'm going to do. So let's go back to the actual handout. So what I'm going to do is just give you a sense of how people are thinking about the causal theory of time in the 70s in philosophy, and explain what I think is the chief difficulty. Lots of problems were raised. Some of those problems are going to seem really strange to our ears. So one of them, which I won't talk a great deal about, is that Smart complains that the causal theory of time or causal theory of space-time uses modal notions. And that we should reject it merely because it's using notions of possibility. That's sort of coming out of a fear of modality that was in the air at the time, that I'm not sure many of us are going to take that seriously these days. What I'm going to do is then offer an alternative causal theory of time. And I'm going to take a look at causal set theory briefly and just sort of use that to motivate the way I'm thinking about the causal theory of time. The main take-home message from this talk, though, really is that there are lots of other ways to build a causal theory of time than the way that was explored in philosophy in the 70s, and maybe we should look at some of those other options. You don't have to like the particular option that I put on the table today, but I think it's worth thinking about other ways of developing a causal picture of time. Okay, so here's how people were thinking about the causal theory of time. At least this is how people like Jack Smart were thinking about it. So it's an identity theory. And I think it's sort of unsurprising that it's an identity theory, because this is sort of during the period when identity theories of the mind are around. And the idea is that spatiotemporal relations, so the sort of metric relations or the distance relations that we have in the space-time, they're identical to causal relations. So it's like a token identity between the individual spatiotemporal relations and the individual causal relations. So I'm just going to assume that these relations are whatever physical distance relations are represented by the metric tensor in the field equations. I'm also going to assume that the identity here is a sort of necessary a posteriori identity, right? Of the kind like water is H2O. In fact, when you look at the view that Smart reacts against, it looks more like an a priori identity, because a lot of the objections that Smart raises are conceivability objections, right? He says that it's conceptually possible for causation and time to come apart. And that makes it really look like a kind of a priori identity that he's thinking of. There are other objections he raises that don't rely on that sort of conceptual stuff. And I'm going to set aside the conceptual picture because I think it's just way too strong. And I think the more plausible version is the necessary a posteriori version. All right, lots of problems get raised by Smart, and there's the interplay between Grunbaum, Smart, and Van Fraassen, which is really interesting. Van Fraassen does a lot to patch the problems, but I think there's one problem that he didn't manage to fix. And this is the problem that I'm going to call the problem of causal indolence. And this problem comes from Smart, I don't think the version of the problem that SMART gives us is a particularly good version of the problem, but I think there is a good version in the neighborhood. So this is what SMART says. He says, it is difficult to see how the causal theory of time is applicable to theories which allow for the existence of events which are neither causes nor effects of other events. It at least seems to me that I can consistently envisage a universe of purely random events spread out through space-time. So what he's saying is that, there is a kind of conceivability argument here, but I don't think you have to rely on conceivability to make the point. I think it's just, you could argue that it's just possible for there to be a space-time that's sort of completely free of causal relations. And if you think that that's possible, then you can't think that there's any sort of a posteriori identity between the causal relations and the spatiotemporal relations. So there are three versions of this problem that you'll find if you dig into the literature a bit. I think the version that SMART gives us is one of the first or second ones, and I don't think those are the great ones, but they're worth having a brief look at. So the first version is, you could think that there are sort of empty regions of space-time. So you could think of, space-time is a completely empty thing, right? Like if you think there could be empty space-times, and maybe you think that that gives you reason to think that there could be space-times that have no causal relations, if you think that causal relations always connect pieces of matter. And if you think that there can be empty regions of space-time or empty space-times in general, then you might think that there's no way to identify spatiotemporal relations with causal relations. So that's one way of getting at this idea. Now, this sort of empty regions version of the objection, I think, is ambiguous between two ideas, and I don't think either of them, like once you sort of think about them, I don't think that there's a real problem here. So one version of the problem is that you think that there are regions without matter fields. And I think that this would just be a mistake in general relativity to think that there's a region of space-time without a matter field. The matter field is everywhere. And in fact, the sort of metric structure is based on the idea that there is this interaction between the matter and the metric tensor. And so it's not clear that you could have something that's empty of matter in that sense. There's another version, though, where you think that the matter fields are kind of zeroed out. So there is a matter field there, but the field values in certain regions, they just take zero values. Neither of these pose a problem because on the first hand, like general relativity doesn't really allow you to have these regions without a matter field. But if the matter field's zeroed out, it's still there to do causal work. So it's not obvious that you can't find some causal relation to identify your spatiotemporal relations. Maybe you have to do something like say, well, there's a possible relation there or something like that. And that is what Grunbaum does, actually. He uses a kind of modal notion. But it still seems that you can find something potentially to identify with the causal relation, some causal relations to identify with the spatiotemporal relations. The second version of the problem, and this is the version I think that comes closest to what SMART gives us. You could think that there are events that are time-like separated, but that aren't causally linked. So you could think that there's sort of two, I raise my hand here, and far off in a distant galaxy, a star goes supernova. And you might think that there's just no causal relation between those two things, despite the fact that they are time-like related, so long as the star going supernova is sufficiently in the future to be in my forwards light cone. And if you think that there's no sort of causal relation between those two things, or there might not be a causal relation, then despite being time-like separated, there's no causal link, and so you can't identify the spatiotemporal relation with a causal relation. It's not clear that this is a genuine physical possibility. It looks like it looks again like a kind of mistake to think that there is no causal relation, particularly if you take the theorems from Malamud and Hawking seriously, because those theorems really are about the time-like separations. It's the time-like connections that seem to give you this sort of causal structure. And it looks like I am causally connected to that far-off event. But maybe I'm not the cause or something like that, but there is some causal link between me. It makes some very small difference if you stop me from raising my hand, maybe just not a difference we care about. The third version of the problem, and this is where I think things really do get interesting. Relativity seems to tell us that there's no physical signals that transmit between space-like separated events. And this is generally interpreted as a kind of blanket ban on causal action at a space-like distance. So there's not going to be any causal relations between me and things that are on my simultaneity hyperplane. But space-like separations are still spatiotemporal links, right? They're still part of that metric structure. And so if you think that there are those space-like separations, and that causal relations between them aren't physically possible, then it does look like you've got a problem. You can't identify there's not even any possible causal relation between two space-like separated events that you could identify the spatiotemporal link with. So, and again, this is kind of unsurprising when you look at these theorems from Hawking and Malamud, because they do focus on that light cone structure. And it's that sort of partial order structure that the sort of causal structure embedded in the light cone that they use. But that causal structure in the light cone is not extending between space-like separated events. So, if you think that the spatiotemporal relations, there are physical distance relations corresponding to everything in the metric structure, then there are going to be some spatiotemporal links that just aren't identifiable with causal relations. And that does look like a problem. All right, so the problem, I think, motivates moving away from an identity theory. And there's a question about where we should go from the identity theory. I think that I don't think the identity theory is completely sunk. There might be versions of the identity theory that do better. But I'm going to look at a non-identity theory. And so the basic idea is identity is a really strong relation. Lots of other relations kicking around in metaphysics that we could use to connect spatiotemporal and causal structure. Maybe one of those other relations will do better. I'm actually going to skip over the detail of causal set theory because it's not super important for what I need. Basic idea is that the fundamental structure is a partial order over discrete sets. The entire universe can kind of be represented as a Hasse diagram, so one of these branching order structures. It's not a metric structure, although maybe you can impose a metric over it, or maybe you can get some kind of metric structure out of it. There's also, so the dynamics of it involves a law which tells you how each of these points sort of comes into existence, how you get, say, node 2 from node 1. It's that law of sequential growth that some people interpret as the flow of time. I am inclined to think that the physicists are over-interpreting their own theories in this case. I think that you just have a kind of static partial order representation. And yeah, you can sort of think of it as unfolding, but it's not obvious that there's any physical reason to think of it that way. What's important for my purposes is that there's no spatial temporal or spatiotemporal metric structure in causal set theory. The sort of fundamental physical description doesn't have any kind of space-time in it. Nonetheless, proponents of this view think that spatiotemporal relations are emergent and that they come out of this underlying causal set structure. And it's basically this notion of emergence that I want to suggest is one way that we can think of a causal theory of space-time. So rather than think of it as identity, we can think of it as some kind of relation of emergence, which is often associated with not being an identity relation. So the particular version of the view, and as I said, you don't have to buy the particular version of the view that I'm putting forward. I think if you just can see the idea that maybe we should be thinking of things other than identity, I'd be happy enough with that. But the actual version of the view that I'm going to put forward is a version that uses a grounding relation. So I'm going to understand grounding in a very loose sense, and that's the sense described by Dasgupta and Karen Bennett. Grounding, I think, is just a word that we have for a bunch of relations that are in the family of ontological dependence relations. Things like composition, constitution, even some people think like determinate, determinable relations, truth-making relations, these sorts of cases where it doesn't look like there's a causal dependence, but there's some kind of dependence. So the thought is that you've got two structures. You've got a causal structure, a fundamental causal structure. You've got a non-fundamental spatiotemporal structure, and the non-fundamental spatiotemporal structure is grounded in, but not identical to the causal structure. And this is similar to some theories of mind, where you think that mental states are determined by or grounded in or supervenient on, if you want to go old school, on some kind of physical states, but they're not identical to them, right? They're different states. On this picture, causal relations are more fundamental than spatiotemporal ones. So the idea is that causation is the fundamental structuring relation of the universe, and spatiotemporal relations emerge from that causal structure under certain conditions. And it's sort of important to add that rider because the causal set theorist thinks that not every causal set gives you a space-time. Only very certain ones give you a space-time. And so I think we need the idea that not every sort of causal structure is a spatiotemporal structure. There may be non-spatiotemporal causal structures. If you want to know more about that, we can get into the metaphysics of causation a bit later. I just want to focus on this problem of causal indolence, though. So I think that on a very simple reading of the non-identity identity theory, the problem doesn't really go away, because you might think, well, look, there are no causal relations between space-like separated events, and so we don't really have any causal relations that are available for identity or for grounding. There's just sort of nothing there that we can use as the foundations for these spatiotemporal connections. But I think the problem can be addressed because grounding relations are more flexible than identity relations. And in particular, you can ground relations in absences at a more fundamental level. So for instance, think of the fact that you're a member of a club, just in case you're not biologically related to any of the existing members. So in this case, you've got a relation, your membership relation, being grounded in the absence of some other relation. And that's how I'm going to think of the connection between some of the spatiotemporal relations and some of the causal relations, that some spatiotemporal relations are actually going to be grounded in the absence of causal relations at the fundamental level. So, you know, this sort of pattern of causal presence and absence grounds a structure of spatiotemporal relations, space-like and time-like connections. Okay, so this is the sort of first pass refinement of this theory. Spatiotemporal relations are grounded in a pattern of more fundamental causal relations. Time-like relations are grounded in the presence of fundamental causal connections. So wherever there's a fundamental causal connection, you get a time-like relation coming out. Wherever there's no fundamental causal connection, you get a space-like relation coming out. That's the sort of first pass attempt. The problem with this is that's a little bit too weak, because anything that happens to not be space-like connected to things that are space-like connected or time-like connected to one another will end up being spatiotemporally connected, and that might not be exactly, sorry, anything that's not causally connected might end up being spatiotemporally connected. And that's not exactly what you want. So for instance, if you think mathematical objects are not causally connected to anything physical, then you're going to end up with saying that they're space-like connected to physical events as well by this first pass refinement. So we need to go a little bit deeper. What we need to say is something like, you've got a causal structure, and in order for the space-like separated event, the space-like relations to be grounded in that causal structure, sorry, let me take a step back. Everything in your causal structure that can ground spatiotemporal relations is causally connected to something else, right? So the idea is that we start with a kind of causally closed system where everything is causally connected by some relation to something else. So that doesn't mean they have to be directly causally related. It doesn't mean they have to, like, everything is causally related to everything. It just means that everything stands in some causal relation to something else, right? So you don't have any kind of causally isolated pockets. And the idea is that that's your grounding structure for space-time. So it has to be causally closed in that sense. And that way mathematical objects get pushed to the side because they're not causally connected to anything in space-time. And so they are sort of causally isolated bubbles. And so the space-time, spatiotemporal relations can get grounded in that causal structure. So then we get this, I'll just skip down to this sort of refined non-identity causal theory. So this is the sort of final theory as I'm thinking of it at the moment. Spatiotemporal relations are grounded in the presence or absence of fundamental causal connections between events that are embedded in a causal structure. And that means that they have to be causally connected to something, even if there are things that they're not causally connected to. That causal structure has to be governed by laws that qualify it to be a grounding base for space-time. And so what I mean by that is this thing that the causal set theorist said, that not all causal structures give you space-time, and presumably that's got something to do with the laws of physics about which causal structures are going to be the ones that give you space-time. So whatever those laws are, they're going to constrain the grounding base for space-time. And the laws over that structure are also going to determine sort of the presence or absence of causal connections. And so you get space-like relations depending on the absence of causal connections, like I said before, time-like relations depending on the presence of causal connections, but then the entire causal structure ensuring that you don't have any causal isolation that gives you sort of erroneous space-like or time-like connections between things. And that is the way that I've developed the view so far. The picture is, there's a lot to sort of explore about it. One thing is, what is causation in this context? What does it mean to say that causation is fundamental? And we can have a chat about that if you like. But basically the core idea is that we need to at least think about moving away from identity and moving towards something a little bit more exotic for developing our causal theories of space-time. And the physics, I think, is motivating us to do this to a certain extent. Okay, thanks.
Thanks, Sam. Does anyone have any questions? Peter?
Thanks, Sam. That's super interesting. And I want you to say a bit more about one of the last things that you said. I was actually going to ask you, and then you brought it up. So it means that causation needs to be fundamental. And then you said, kind of, maybe we can talk about that. What were the things that you were going to say about causation being fundamental?
Yeah, so the trick here is that if you look at lots of metaphysical theories of causation, they build space-time in from the very beginning, right? So you think about Salmon and Dow's Mach transfer theory. Causation is a transfer of a conserved quantity between world lines in space-time that intersect. Think about Lewis's counterfactual theory. The semantics for counterfactuals involves matching for regions of space-time. Hume's regularity theory, causation is regularities in space-time, right? So all of these have like spatiotemporal notions and foundations. One that doesn't is Woodward's interventionist picture. It doesn't look like he builds in space-time because he's not giving a reductive account of causation, right? He's saying, look, causation is connected to intervention and manipulability, and there's no sort of at any point, any sense that he's analyzing causation in spatiotemporal terms. It's at least compatible with his theory that interventions could operate on things that aren't spatiotemporally located. And so I guess the way I think about it is one way of interpreting Woodward's picture, although I don't think this is how he would put it, is that causation is a primitive notion. It's not one we can metaphysically analyze. It's definitely not one we can metaphysically analyze, on my view, in spatiotemporal terms. It's just the basic notion, and that the rest of the universe comes out of that. And then we can give an account of causation insofar as we want one in the interventionist framework as being the way that the sort of space-time free picture of causation.
Yeah, thanks. That's actually, that answer was interesting, more interesting than I was expecting. That's maybe we can chat about that later. I find that very interesting. Yep.
Any other questions?
Yeah, I could potentially raise one. This is actually kind of in relation to what you were just saying about causation being primitive, but obviously the kind of intuitive first pass idea about why causation wouldn't be is it feels like, causation needs to involve something kind of changing your behavior somehow or making you do something different. And I wonder whether under this account you could have something that is causally related to something without changing its behavior in any way. This is kind of primitive causal relation, and that is sort of established on its own before you even ask any questions about what the behavior of either of the things is or what they do, which seems kind of interesting if you're talking about a bunch of things as being causally related to one another, even though kind of nothing happens as a result.
Yeah, so I guess the way that I think about a causal relation is in interventionist terms. So basically, I just think that there are a bunch of modal links between things, right? So like start with matters, like bits of matter in the void, right? And those bits of matter have modal links between them such that if I wiggle this one, then this one wiggles, right? That's all I'm thinking of. That's sort of, I take the core interventionist idea. And in Woodward's picture, the sort of like modal stuff is more fundamental in some sense, right? Like all of those modal links are basic, but you can have a completely static picture, right? Where nothing changes because, as a matter of fact, nothing's ever wiggled, right? It's just that if you were to wiggle things, then other things would wiggle. But it is compatible with kind of like changelessness in that sense. I don't want to analyze causation in terms of change. I want to do what Woodward does, which is analyze it in terms of interventions, insofar as you're going to analyze it. Although that's circular for him because he thinks an intervention is analyzed in terms of causation. But I'm happy with that.
Good. Any other final questions? Well, good. Well, then if not, I might get everyone to thank our speakers for such great talks. A lot of overlap, which is good. And then I think we might finish up a couple minutes early.
Thanks,
Great.
everybody.
Thank you, everybody.
Thank you.
Thank you.
Thank you. All right, I'll see everyone in the next sessions.
Is that